welcome to this module, and actually this module is a short module on a very important process in microfabrication called etching, right. So, we will see why it is important and what kind of etching methods are there. Now, why we are learning this is a part of this course, because when you want to develop an electronic system, that too for certain diagnosis of a disease, in some of the systems we are using a micro engineering technology. And when we talk about micro engineering technology, along with few processes like thermal evaporation, e-beam evaporation, you have wet etching, you have dry etching, you have photolithography, you have e-beam lithography, you also have the chemical vapor deposition techniques like CVD, LPCVD, PECVD, MOCVD, right, APCVD. So, a lot of techniques are involved, and one of those techniques is wet etching. And when we talk about wet etching, we will see why it is important, and if I talk about dry etching, why it is important. So, this module is on etching the materials in the case of microfabrication. So, if you see the slide, we will be talking about etching process. The first process is, let us see, etching is a part of pattern transfer process after lithography, right, which removes material selectively. Here I have given you an example of a basic patterning process. So, if you see, we start with a wafer, right, we start with a wafer, then we deposit a film. Now, how you can deposit the film? Now, you should be you should know what are the methods for depositing this particular film. There are two methods, one is PVD, second one is CVD, right. And in PVD we have thermal evaporation, we have e-beam evaporation, we have sputtering, right. In CVD we have LPCVD, we have MOCVD, we have PECVD, we have APCVD. Now, once the film is deposited by any of the technique, right, you can also use spin coating, you can also use spin coater for spin coating the film on the wafer. So, using any one technique, if we deposit a film on the wafer, and if I want to pattern the film, what kind of patterning I want? I want to pattern the film so that finally I only have this particular structure, that is, at certain point film is there and certain area the film is not there, right. So, how can I etch the film in this area? All right. So, for that we have to first deposit a film on a wafer. We will perform a photolithography. How can you perform photolithography? By first using photoresist, right, and then doing lithography. After doing that, you can see that if you do the lithography, what you see here is photoresist is not saving the area which we want to etch, and the remaining area there is a photoresist is not covering the area where we want to etch. So, now if I dip this wafer, in a chemical, what kind of chemical I can use? Based on the film that we need to etch, right. Suppose if the film is silicon dioxide, then what chemical I can use? I can use buffer hydrofluoric acid, right. So, different chemicals are there for different films. So, when we dip in when we perform lithography and dip the wafer to etch it, you will see that the film will get etched from the area which is not protected by photoresist, and the area which was protected by photoresist, the film is still intact. After that, we have to strip off the photoresist, and stripping of the photoresist is done using acetone. We already remember, right, stripping of photoresist during acetone, right. Finally, when you strip off the photoresist, right, like here, you can obtain your film. This is the wet etching technique, okay, or you can say a dry etching technique. So, I will tell you in detail what are wet etching and dry etching, but before that let us take an example. So, you understand in detail. The figure of merits for this one are etch rate, selectivity, directional anisotropy, directionality, anisotropy, defect, cost and environmental safety. These are some of the figure of merits. So, if I take an example, let us take an example where we want to fabricate a pressure sensor, fabricate a pressure sensor, right, which will look like one that I am drawing right now. So, all right, and then on this we want to have piezo resistor. So, now what exactly these things are? So, I will just make piezo resistors like this, right. So, what are the areas? The first area is silicon dioxide, which is right over here. This is also silicon dioxide, right. Here is silicon dioxide, this is silicon, this is chrome gold or interdigitated electrodes made using chrome gold. This one is our piezo resistor. Okay. This is what I want. This is what I want using photolithography, and etching. Okay. So, to obtain this particular device, right, what are the steps and how etching is important, that is our today's module. Okay. So, now what do you see? You see a silicon wafer, right? You see a silicon. So, we will start with a wafer and we say that we are starting with a wafer, all right. This is my silicon wafer. The next step is I have to grow silicon dioxide or deposit silicon dioxide, right. So, if I deposit silicon dioxide using thermal oxidation, SiO2, right, and this is my silicon. Next step is I will deposit a metal on this silicon dioxide, right. I will deposit a metal on the silicon dioxide so that I can obtain my chrome gold interdigitated electrode, right. So, I will deposit chrome gold, this is my chrome gold, right, and then remaining things are silicon dioxide, silicon dioxide, right. Next step, in the next step I have to spin coat photoresist. I have to spin coat photoresist. So, let us use blue color to show our photoresist, all right, and let us use this pattern. So, what is this one? This is my positive photoresist. Then what else I have? I have silicon dioxide. Here also I have silicon dioxide, right. this is silicon, and then what do I have here? I have chrome gold, right. This one is chrome gold, right. What is the next step? Next step is we have to use a mask. We have to use a mask. So, I will draw quickly wafer, oxide, right, oxide, then we have chrome gold, right, chrome gold, then we have photoresist, which is positive photoresist, and we have spin coated this positive photoresist and cure it at 90 degree. Okay. This is spin coated photoresist, and we have done soft bake at 90 degree for 1 minute. On this we have to use a mask, right. So, let us use a mask, and mask is such that I have to only protect the interdigitated, I want to pattern interdigitated electrode. So, my masks would be, my mask would look like this. It is a bright field mask. Field is bright, pattern is dark, it is a bright field mask. Right. So, this is my bright field mask, right. What is the next step? Next step is we will expose it, we will expose it with UV light, UV light, right. After exposing, what we will do? What is the next step? Next step is to dip this wafer, the wafer in photoresist stripper or photoresist stripping solution. So, or in another terms it is also called photoresist developer, not stripper. Let us use this correct term. It is not called stripper. Stripper is when photoresist will be stripped off. We are using photoresist developer, right. So, when you dip this wafer in a photoresist developer, what you will have? You will have oxidized silicon wafer, on that there is a chrome gold, on that you have photoresist, but this time photoresist is developed 1, 1, 2, 3, 4 and 5. Right. This is my positive photoresist. All right. Now, I will perform hard bake. Hard bake is done at 120 degree centigrade for 1 minute on hot plate. When I go for hard bake, what is the next step? Next step is I will dip this wafer, in chrome gold etchant. First, what is the top layer? Top layer is gold, bottom layer is chrome. So, first I will etch the gold from the wafer, and then I will rinse the wafer with DI water. Then I will place the wafer in a chrome etchant, right, and it will etch chrome. It will etch chrome and gold only in the area which is exposed to the chemicals. The area which is protected by the photoresist will not be etched. This etching of chrome gold using a chemicals is called wet etching, because we are dipping the wafer in a etchant, in a chemical. Now, if I do that, what will I have? if I etch the chrome and gold using wet etchant, what will I have? I will have chrome gold, I will have chrome gold in this area, right. So, you see here the chrome gold we can fabricate or we can pattern using photolithography and wet etching. Alright. What is the next step? Next step is we have to pattern piezoresistor. So, to pattern piezoresistor, let us see. We will take again, we will start from the chrome gold and then we will continue. So, we have oxidized silicon wafer, right, and on oxidized silicon wafer we have chrome gold in the patterned way, which is called interdigitated electrodes, which is called interdigitated electrodes. So, let us see, we have chrome gold like this, right. This is my interdigitated electrodes, alright. Rest you know, this is silicon and then the two bottom and top part of the silicon is silicon dioxide. Now, on this what I want? I want a piezoresistor. So, what I will do? I will spin coat P dot PSS. What is this material? This material that I am spin coating is PEDOT. Let me write it down because in the top part of the screen we have little bit problem. So, I will just write it down again, right. This is my piezoresistor film or piezoresistive film and this is nothing but PEDOT PSS. This is my conducting polymer which acts as a piezoresistive material. The next step here is I have oxidized silicon wafer because I have oxide in the bottom part, oxide on the top part with interdigitated electrodes on top of it, right, and then on that we have P dot PSS which will act as a piezoresistive material and we need to pattern this material, right. We have to pattern this material. So, this is my piezoresistor or piezoresistive material, right. There is a chrome gold inside. On this what we will do? We will deposit or we will spin coat, rather we will spin coat positive photoresist. This is my positive photoresist, right. Remaining you know interdigital electrode P dot PSS, silicon dioxide and silicon. After spin coating positive photoresist, the next step is to use mask, right. We have to go for soft bake, of course, soft bake positive photoresist, you know, 90 degree 1 minute hot plate, and then on this I will load a mask. So, I will just delete this one for now, and let us show a mask, right. So, how should a mask look like? If you go back, you want piezoresistor only in this area, right. So, we have to protect piezoresistive material only in this area. For that we have to have a mask which will protect my piezoresistive material in the area of my on the desired area, that will help me to get the piezoresistive piezoresistor, right. It will not help me to get piezoresistive, it will help me to get or pattern piezoresistor. This is my bright field mask. Okay. Now, you understand this thing, why I have used bright field mask. because I have here positive photoresist. Now, what is the characteristics of positive photoresist? That the area which is not exposed by UV light will get stronger. The area which is not exposed by UV light will get stronger. So, now you can see that the area that is in black shade will not get exposed and the area which is in white shade will get exposed, right. So, after this the next step would be that I have to go for, after this I have to remove the mask and then do a hard bake. Hard bake is done at hard bake. Okay. Hard bake is HARDBAKE, hard bake. Hard bake is done at 120 degree centigrade 1 minute on hot plate. Easy, right. So, now next step is, after hard bake, our next step is we have to dip this wafer, in photoresist developer. When I do that, what will I have? I will get, let me draw it little bit here, okay, like this. My silicon dioxide layer is intact. On that, my chrome gold layer is also intact, or chrome gold pattern, interdigital electrodes, right. On that, my piezoresistive material is still intact. Piezoresistive material is still intact, but my photoresist layer will be patterned now. So, I will have a photoresist only in this area, right. So, this is my photoresist. What is the next step? Next step is that I will dip this wafer, I will dip this wafer in we missed step actually. We have used hard bake before photoresist developing. That is not a correct statement. So, let us understand what I mean. After positive photoresist, you have to do soft bake, then you have to expose the wafer with UV light, of course, after loading the mask. Once that is done, you have to develop the wafer, and after developing the wafer, you have to go for hard bake. Okay? You do not have to do hard baking before you develop the wafer. Okay. So, that you can do only when you are using SU8 material. In case of positive and negative photoresist, you have to go for soft bake. After you spin coat it, after soft bake, the next step is loading of mask and UV exposure. Next step is photoresist developer. Next step is hard bake. Next step is etching. Alright. This is in case of positive and negative photoresist. Right. So, what we have to do after the UV exposure step, we have to load the mask. After photoresist exposure step, we have to develop the wafer or develop the photoresist, and then after photoresist is developed, it will look like this particular pattern, followed by which we have to do hard bake at 120 degree centigrade for 1 minute on hot plate, followed by etching P dot PSS, Again, you see, etching is very important. When you etch P dot PSS, what will happen? You will have a wafer, oxide, because the etching chemical or material will not affect oxide or will not affect the chrome gold interdigitated electrodes. Okay. So, that is why we do not worry in this case, and we do not have to go for the lift off technique. I have explained you lift off. this is my piezoresistor patterned, this is chrome gold, interdigitated electrodes, silicon dioxide, silicon, silicon dioxide, right. So, again we have used etching. So, where are we now? We have done IDE and we have patterned the piezoresistor material. Next step is we have to do this bulk etching of silicon, bulk etching. Let me go for the one more slide where I can show you the next step, where we have to create a diaphragm, right. So, what we have? We have oxidized silicon wafer, all right. On oxidized silicon wafer we have chrome gold, on chrome gold we have P dot PSS, right. This much we have. Now, we have to etch the silicon wafer from back side, from the back side. So, what we will do for that? We will spin coat photoresist, we will spin coat positive photoresist, right. Then we will do or perform soft bake process step. After soft bake, we will load a mask such that my photoresist will protect the area of my interest and the remaining area will be etched after I expose this wafer with UV light and develop it in the photoresist developer, right. This is my bright field mask, right. After this, what is the next step? Next step is we have to expose the wafer, in UV light, right. After exposing the wafer, next step is we have to unload the mask and we have to dip this wafer in photoresist developer. If I dip the wafer in a photoresist developer, what will happen? I will have photoresist in this two area and this area is exposed now for further process. So, now what can I do? I have to go for hard bake, right, photoresist developer, then hard bake. After that, I will deposit this wafer in I will not deposit, I will etch silicon dioxide by dipping the wafer in buffer hydrofluoric acid, all right. So, when I dip the wafer in buffer hydrofluoric acid, what will happen? I will have silicon dioxide only here. I have silicon dioxide only in this particular region, right. Why? Because other area was protected by positive photoresist. So, now when I am etching silicon, again we have to use process called etching of silicon dioxide, that we have used which kind of etching? We have used wet etching, and the chemicals that we used is buffer hydrofluoric acid. Okay. After this we have to strip off the positive photoresist. So, if I strip off the positive photoresist, I will have this pattern. Now, I will deposit I will dip this wafer in either TMAH or KOH. These are both chemicals, and that is why it is wet etching. KOH and TMAH has some kind of pros and cons. If you want to know, these are the pros and cons. TMAH gives us is a smooth wall when we etch. KOH gives us a rough wall when we etched. TMAH is slower, KOH is faster etching, slower etching. Then TMAH can be done at room temperature or 25 degree centigrade. KOH is done at or carried out at 80 degree centigrade. Alright. So, these are advantage, disadvantage. TMAH is also neurotoxic. TMAH is neurotoxic, or this is as per the research literature survey. Okay. But both things are used, TMAH and KOH, for wet etching. When we dip this wafer in TMAH and KOH, what we will get? We will get a diaphragm like this, and this angle is 54.7 degree, 54.7 degree, right. So, what we got? We got this pattern. Understood? So, this is the beauty of wet etching. We are using wet etching to etch the silicon wafer on which there is piezoresistor and interdigital electrodes, and etching from the back side by removing silicon dioxide and dipping the wafer in wet etchant, which are KOH and TMAH. Alternatively, we can also go for dry etching. We can also use dry etching. Okay. We will talk about that in a few slides. Let us continue this particular module, and here if you see the how there are several things that we have to understand. The first is etch rate of removal of the desired material, how fast we can etch. Okay. So, if I am etching silicon dioxide, what is the etch rate? Chrome gold, what is the etch rate? That is what we mean by etching rate or rate of removal of the desired material. For example, you have D as a thickness, and then you can see that after time t, delta D will be etched from the wafer. So, before etching, after the etching, etch rate can be given by D minus delta D1, D minus this is total thickness minus the leftover thickness, right, divided by the time taken, which we can write as delta D. So, delta D minus D1 can be delta D, and delta D by T is your etch rate. Okay. Now, second is very important thing, which is the etch rate profiles or etching profiles. First is, if we keep the wafer in the etchant for more time than it is required, then you have over etching. If you keep the wafer for less time than the etch rate, then the time required to etch the material, you will have under etching, and if the time is perfect, then we will have intended etch, right, over etch, under etch, intended etch. Alright. So, let me move to the next merit. Next merit is etch selectivity, very important. Suppose I have a resist and there is silicon dioxide and silicon, right. The etchant for silicon dioxide should not affect my silicon. If my etchant of silicon dioxide, that is my buffer hydrofluoric acid, will etch the silicon, then I will not be able to use this particular etchant, and that is why selectivity is very important. So, etch selectivity is defined as the ratio of the vertical etch rate, which is here, right, of the material you want to etch to the material you do not want to etch. So, this is the material we do not want to etch, right, silicon. we want to etch silicon dioxide, right. So, ratio of the vertical etch rate, this is the vertical etch rate of the material you want to etch, that is silicon dioxide you want to etch, to the material you do not want to etch, which is silicon you do not want to etch. So, it should be extremely high, right. So, selectivity is a relative measure, and selectivity can be defined as selectivity of so in this case if you talk about silicon dioxide versus resist material, you can also understand the another way of doing it, that what is the etching rate of the resist material, because you see not only the silicon that we need to protect, but also the photoresist should not get etched, right. If the photoresist get etched, then the silicon dioxide from the area below the photoresist also starts etching. So, selectivity here we have to use two selectivity. First one is selectivity of SiO2 versus resist material, and second will be selectivity of SiO2 versus silicon wafer. So, first one is given ratio of R SiO2 by R resist, and second one is R SiO2 by R silicon. Selectivity comes through chemical reaction between different combination of layers. For etch process we want to have higher selectivity, right, as high as possible. Okay. Let us go to next one, etching figure of merits. First one, directionality versus anisotropy. We need to control horizontal and vertical etch rates in order to get desired profile, right. First thing, very important. So, second one is mostly for any biochip fabrication like microheater diaphragms, interdigital electrodes, we need a diaphragm brick shape which is not isotropic, right. Wet etching provides isotropic etching. So, we can get this kind of etching which is isotropic etching, all right, where it will have this kind of etching where the undercut is there, and it will start etching from the material which is below the masked material, masked layer. Below the mask layer, this material is also getting etched. This is what we do not want in a lot of applications in the microengineering domain. Dry etching provides anisotropic etching, combination of physical and chemical etching mostly used in biochip fabrication. For example, this one is a dry etching technique and it is better because it provides us anisotropic etching. Anisotropic is defined as 1 minus R lateral to R vertical. How much is the lateral etching? Ratio of lateral etching to vertical etching. Now, if you take this particular example, then you can very easily see that the photoresist is on blue color, green color is silicon dioxide, and the orange color is of silicon. Here if the anisotropy is 0, then we will have the undercut which you can see here in a 3D representation, but if the anisotropy is 1, then we have a perfect etching of the desired area. So, this is the importance of the etching figures of merits. Further, if I want to have etch goals, then typically any etching process requires this few points. The first is it should be highly selective, second point is anisotropy, that is approximately 1, third one is high etch rates, and it is difficult to get all three together because it can be like an ideal situation, and there is a trade off between all these interdependent parameters. So, when you use the etching classification in particular, then the etching classification is like this: you have etching, then in that etching you have isotropic etching, anisotropic etching. Further you have physical etching, you have chemical etching, right, and then you also can divide it in this particular format where you have dry etching and wet etching. Okay. Wet etching is the chemicals that we have seen. Dry etching is where you can use sputter etching, you can use plasma ion etching, and you can use reactive ion etching or deep reactive ion etching. Alright. So, we have etching classification. So, like from the isotropy point of view, we have isotropic, anisotropic. From the physical and chemical point of view, we have physical etching versus chemical etching. From the dry etching versus wet etching point of view, we have wet etching where we have used certain chemicals to etch the material, while the dry etching we have further identification as sputter etch, or it is a plasma ion etch, or it is a RIE or DRI. Like I said, RIE stands for reactive ion etching, DRI stands for deep reactive ion etching, right. So, if you see the wet etching in this particular particular slide, what you see is it is the simplest form of etching and we get isotropic etching. Wet etching uses an etchant solution such as acid that chemically attacks the underlying film while leaving the photoresist intact. We have seen in the earlier slide, right, where I was teaching you or showing you how we can fabricate a piezoresistive material, a piezoresistive sensor. There we have used the wet etching to etch the piezoresistive material, to etch silicon dioxide and to etch the chrome gold. Now here for example, to etch silicon dioxide, buffer HF is used, also known as BOE, buffer or oxide etch. HF does not etch silicon or resist, that is why it is higher selectivity. So that is the importance of HF or BHF in case of etching the silicon dioxide, because it is highly selective, it will not etch the silicon. Further, when you see the chemical reaction, this is how the chemical reaction occurs. When you dip the wafer, oxidized silicon wafer in HF, then SiO2 plus 6HF gives us H2SiF6 plus 2H2O, and this guy is water soluble, and that's how you get the silicon dioxide out from the etchant. Now using the etchant. Now as the HF is consumed during reaction, ammonium fluoride as buffer agent to maintain HF concentration is used, and the chemical reaction is NH4F gives us NH3 plus HF. You can see this particular video. Let us first see this thing. First is wet etching provides excellent selectivity, poor directionality, that is it is isotropic, and moderate etch rates. So the question now lies in front of us is how we can get a higher anisotropy, right, because there is a limitation of wet etching, and that is it is isotropic. So if I want to go for higher anisotropic etching, what can be the next step? So let us first see the isotropic etching in this video, and then we will go to the next slide. Okay. Now, since you have seen the wet etching, right, let us see the dry etching variants, and I will not to go in too deep in this particular lectures, because this is how we are using it to fabricate a device. This is not a detail about how exactly the etching occurs. This you should know that okay, there are two different types of etching, and you should have the idea that what is used for or how it is used. Okay. So without getting into deep chemistry, let us see how the dry etching works. So if you see the slide, what you find is when we talk about sputter etch, exactly like sputter deposition with inverse polarity, we can get the sputter etch. So negative bias on the wafer instead of target. When you want to deposit the material, you have to have negative polarity and a bias on the target and positive on the wafer, but when you want to etch it, you can reverse the polarity or inverse the polarity. Sputter etching is totally physical process. Etching is because of bombardment of ions. Sputter etching has low selectivity, that is a disadvantage, because it is a mechanical way of etching, it will etch the material below it. Highly anisotropic, etching rate can be increased by increasing the argon ion concentration, right. And now let us see this video of sputter etch. Okay. So, let us further see the dry etching variants, and the second variant is the plasma etch. So, if you see the slide, the plasma etching where the enhanced version of the discuss sputter etching for better selectivity and higher etching rate. Modifications are like add reactive ions into the plasma. So, if you add the reactive ions like argon plus CF4, then you can etch the desired material. Higher etch rate can be achieved by increasing pressure, but increasing pressure will result in less mean free path. You know what is mean free path? Is a collision between two atoms in the case of vacuum. Higher the vacuum, larger the mean free path, and less the collision, better the film. Okay. So, less mean free path which is affect the directionality. So, your mean free path should be extremely high. Hence, there is a trade off between higher etch rate and anisotropy. Okay. So, that is the trade off that you need to understand, that either you want higher etch rate or you want isotropic or anisotropic etching. Plasma etching is combination of physical and chemical etching. By adjusting the pressure and DC bias, we can completely remove the physical etching component. However, that is etching can be considered as chemical etching or wet etching. Plasma etching like chemical wet etch has excellent selectivity, poor directionality and moderate etch rates. This is the second type of etching. The first type of etching we have seen is the sputter etching. Then we are talking about plasma etching. Let us see one more kind of etching, and that is called the RI or DRI. But before we go that, yeah, you see here that its etching trade off is, if the material is highly selective, then you have to which one you have to say, go for, and if the material is a low selectivity, which one you have to go for. So, high anisotropy, then you can have low selectivity, but if you have low anisotropy, you can have a higher selectivity, and that is why we said this is a trade off. So, wet etching, plasma etching, chemical etching zone, you can have low anisotropy and high selectivity, but if you want to have high anisotropy, then sputter etching and physical etching zone is a better way to go for. Now, in a dry etching variants, let us see the third one, which is our reactive ion etching. In reactive ion etching, special case of plasma etching, enhanced plasma etching, so if it's a special case in of plasma etching and enhanced plasma etching, where every time RI process is customized, is unique to film being etched, resist material and etch top layer. So, either you want to etch the resist material or the film or the silicon. This RI has a customized process. Many RI mechanisms to understand actual etch process and mathematical models to predict etch rates exist. Side wall passivation increases anisotropy by protecting side walls. So, what happens is, once you send the etching gas, then it will etch it, and then you use another chemical to smooth the side walls. Okay. So, first you etch and then you smooth the side walls. This process keeps on repeating. So, side wall pacification can increase anisotropy by protecting side walls, and hence results in vertical anisotropic etching. So, in this case you will have a perfectly fine vertical anisotropic etching, and side wall pacification is one of the two key steps of deep reactive ion etching. Like I said, first it will etch, then it will protect, then it will etch, again it will smoothen. So, this keeps on going on. And the deep reactive ion etching, the Bosch process developed by German company Robert Bosch in 1994. Bosch is so this is also caused the Bosch kind of etching, and deep reactive ion etching illustration is shown in this particular video. The main idea of DRI process is that the etching of silicon can be used can be done using SF6 and isotropic etch, and generation of polymers for side wall passivation can also be done using the DRI. Based on the required etch profile and material used, some iterations can be provided. So, if you see the DRI in this particular video, also in the next video you will understand how it is done. Let me play the video for you. Okay. Let me play one more video where you will see the details about how the etching is done, and that will be the end of the DRI process. So, in principle what I wanted to show it to you is what kind of etching mechanisms are there. In basically there is wet etching and dry etching. In dry etching you have seen sputter, plasma, and now you are looking at the DRI. So, let me play the video and then we will end the module.
Welcome to the STS room. We're going to explain you a quick overview of how to operate the STS machine. So the first thing to do is once you arrive here into the room is to check the tag to see if the CDO is off, or otherwise if the machine has any problem and cannot be operated. In case that the tag is down or like hidden, you can operate the machine normally. The first thing to do is like come next to the screen of the room, to the small laptop, and log in. Once you are logged in, you have to proceed to the gas chase next to the STS room. The first thing to check in the gas room, the gas chase, is like the CDO box. The CDO box is responsible of neutralizing the exhaust gases from the STS. So by burning them, it makes them harmless. The thing that we have to check is that all the lights are green, and the temperature it's within parameters, as well as the levels of the water, nitrogen, and oxygen. Once we check that everything is under working conditions, we will check if the operating gases are flowing. As you can see, the gases are in this side of the room. We're going to be using the first four gases that are the C4F8. So we have to check if it's in use. Then the SF6, the oxygen, and the helium. If once you arrive here, you notice that any of the tags says that they are not in use, please contact a super user or staff to turn them on. Once you are inside the room, take advantage to check for any weird noises or like funny smells. If everything is in place, you can proceed with operating the machine. Back in the STS room, the first thing that we will do is check the STS tower, and then we will record the conductivity of the water and the temperatures on the STS, the HCU 5 and like 3 and 1. So we will record the values, and once we have recorded the values from the tower, we will go to the computer to record the other different values that we have to record. The ones that we need are going to be the high vacuum pressure, the Kapman pressure, the 4-line pressure, and the load lock pressure. If you have any problem finding any of the values in the screens, you only have to go on top of them to see what are their values. Once we recorded the parameters, the first thing that we have to do is change the operator mode on the software of the STS. In order to do that, we go to Edit, Operator Mode, and we change from Monitor to Development. We press Change, and then we log in the password. We press Return twice, and we change now to Development Mode, where we can operate the machine. Now the first thing to do is to load the desired wafer to the load lock chamber. We do that going to the transfer window and pressing Vent. Once we press Vent, we have to wait for the load lock chamber to reach atmospheric pressure. Once the transfer chamber is under atmospheric pressure, we open it, and we will charge the desired wafer into the chamber. As you will see, like usually the wafers have a flat, and loading carousels we have a small line. Please align the flat with the line on the desired spot. Once we have wafer properly load, we close the load lock chamber, and we go to the transfer window and we will press pump and map. Now the load lock chamber is going to be put under running conditions, and it's going to also scan to see where are the wafers placed. Once the software has mapped the slots in the carousel, we will load the desired one. In our case, we have our wafer in the slot number 1. We just have to press load, and now the machine is proceeding to load the wafer into the chamber. Once the wafer is loaded into the chamber, we have a flashlight here in the machine to check that the wafer has been loaded properly, so we have to turn on the light and check through the window that the wafers is placed properly and the clamps inside the machine are holding it on place. Once the wafer is loaded into the chamber, we have to proceed by selecting the process that we will use. We have 3 standard processes: process B, process A, and auto-clean. In this case, we're going to use the auto-clean. You please press select, don't press process, otherwise you will go straight ahead into processing the wafer. Please press select, and while the machine is selecting the process, you can press the recipe button to modify the values of the recipe. In our case, in that second menu, because it's only an example, we're going to use only like 2 minutes of auto-clean. And also, I'm going to show you how to perform a helium leak-up test. You should do that like probably at the first round of your day to check that there's no major leak of helium coming from the cooling side of the wafer. In order to do that, you press enable, don't touch anything else, and just save the recipe. Once we save the recipe and the recipe has been selected, you only need to press process. As we can see, now the gases are stabilizing. As we can see here, we have the wafer inside the chamber, and also we have like pale blue, that it just changed it to magenta. When we see that change of color, means the process just started. When the process starts, we will have to record the remaining values in the log. They are the 4 gas fluxes, the C4, F8, the SF6, and the oxygen. In our case, the auto-clean only use O2 flux, so only have a flux of oxygen. We also will have to record the cold generator power that is placed here and the platen edge. We will have to record the cold generation for passivation and etching. In our case, we only have for etching. We also have to record the APC and the process pressure, and if we did a helium leak-up test, the helium leakage. If you have any problem finding any of the parameters, you can only leave the cursor on top of the window, and a yellow window will pop up telling you what is displaying. Once the process has completely finished, you will see that the wafer color will change from brown to green. Once that is done, the next thing to do is just unload the wafer. It's very easy. You go to the transfer window and press unload, and we'll see how the wafer is gonna be returned into the load lock chamber. Once the wafer is in the load lock chamber, the next thing to do is to press vent and wait until the chamber is into atmospheric pressure. Now the load lock chamber it's back into atmospheric pressure, so we open it, we grab the wafer that we just processed, we put it in our box, wafer box, we keep it in a safe place, and the next thing to do is put the carousel chamber into standby pressure. We do that by clicking pump only into the transfer window. because we won't be processing anything else, and nobody is after us. We will go to the edit menu, go again to operator mode, and press monitor to put it into standby. Once we've done that, the next thing to do is to log off from the laptop. So that's it for like the operation of the STS. If we have any doubts, please contact staff, but you can also check the SOP for the STS and also the complementary videos that explain more in detail each step of the operating procedure.
Okay. So, what you understand, you understood, I hope you understood that why etching is so important in the case of microfabrication, in particular this device fabrication technology. And the next in lecture I want to show it to you what kind of electronic systems are there that we, or electronic modules you can design so as to interface with the sensor, and that is how your electronic system can be can come into realization phase. So, you are looking at the fabrication where you are developing some sensors and chips, but what to do with those chips? You have to integrate those chips with some kind of electronic module for further processing. We also say it as a signal conditioning circuits. Okay. So, till then you see this video once again, and if you have any question, feel free to ask me through forum, right. My TAs or me, we will be able to answer your queries to best of our abilities. Till then you take care, and I will see you in the next class. Bye.